just 100 feet of your curve. Now you may be at you. Now horizontal curves are very rarely less than 100 feet in length, the arcs. But let's say you may have a problem in the PXM where you have a very small road, local road, low volume, and or it might be a trail or a bicycle path design, like a shared use path design, right? So you have a radius of, I'm sorry, an arc that may be just 90 feet long or 50 feet long. And you're being asked to find the degree of curvature. But your degree of curve, you know it's measured on 100 feet. So in that case, in that very rare case, your degree of curvature, you're going to have to almost like extend your arc, right, to find your degree of curvature. But anyway, the formula to find the degree of curvature is shown here is equation 79.8 of CERN. And it's simply 360 degrees times 100 feet divided by 2 pi r. Now, you don't need to remember the entire equation. All you need to know is that your degree of curvature is 5729.6. A lot of people use just 5730 over r. And that will be your degree of curvature. Now, the concept of the degree of the curve is based on an arc of 100 feet. So therefore, when the degree of the curve is related to an arc of 100 feet, it is said to be calculated on an arc basis, which is shown in equation 79.8. The ratio of 360 degrees to 2 pi is equal to the number of degrees per radian. A radian is a unitless number, so the end result is in degrees. Your degree of curvature is going to be in degrees. When this is multiplied by 100 feet, or what equals 1 station, and divided by the radius of the curve, the resulting degree of curvature is the angle subtended by the arc between stations. So now you see the reason why the degree of curvature is divided by 100 feet is because 100 feet means 1 station when you do a transportation engineering. 100 feet equals 1 station. So it's almost like telling you the degree of curvature per each unit, right, on the road, which is that 1 station, per each unit of length in the road, which is 1 station. Key thing to understand here. The values used in equation 79.8 must be in US units. The degree of curvature is a concept that is only used with US units. There is no parallel concept in metric highway design. No parallel concept to the degree of curve in metric unit design in SI units. So guess what happens to your equations if you're given information for a horizontal curve in the metric system? You can't use that one. You can use that one. You cannot use that one. Then you can use this one. Now, if you want to use these equations, you may want to convert the units into feet, into the US system, and then use these equations, and then convert back to the metric system at the end. However, I don't think that'll be necessary in the breadth portion of the exam, because that really is a big roundabout way. But you know, as I said, NCS has a carte blanche when it comes to horizontal circular curves, so they may test you on something like that. But I think that will be very rare, but it's something that you should be aware of. If you are given a metric problem in horizontal curves, and you start using the arc definition or the degree of curvature concept, there's a very, very high possibility that you are in the wrong track, that you have veered off the road and now are out in the weeds. You probably may need to use a combination of these equations to solve for a metric type problem. Just keep that in mind. Now the degree of large curves. Now when you have curves that have very large radii, short portion of the curves are essentially straight. And one good example are railway curves or even highway curves. So when you have very big curves with large radii, you can use equation 79.9, which are based on the chord. And this also comes from AASHTO. Now, how do you know the breakpoint? When is it a large curve and when is it a small curve? Well, when the radius of the large curve is greater than 1400 feet on average, the difference between the arc and the chord basis is negligible. Now, this is not a standard. It is just a mathematical approximation. It's not that the other formula is not going to work. It's just that this simpler formula will just give you a number that's very close to the true to the form circular geometry number from the previous equation. And that typically occurs when you have a radius that is greater than 1400 feet. It is a mathematical approximation, not a standard, not a reference, not a code thing. It's just a simplification because of the mathematical approximation. And when you have a very large radii, your tangents become, your curve segments start to become almost straight. Another key concept when it comes to horizontal curve design is that of stationing. Now, stationing is simply a way to quickly reference large numbers in highway or railway design, because you have long distances for this, big highways or railroad lines that travel, you travel through long distances. So it becomes kind of cumbersome to call everything, oh, you are at a distance of 1200 feet from the point of beginning of the curve, or you are at a distance of 58, 4400 or whatever, right? Long number. So a way to simplify that is by basically getting rid of your last two zeros. So if you're at a distance of 100 feet, you are at station 1. If you are at a distance of 1,000 feet, you are at a station 10. If you are at a distance of 10,000 feet, you are at station 100. This is applied to any point, and the position will be given by the total distance from the beginning to the current point. Station 0 plus 0, 0 is called station plus 0, 0. If you are at 100 feet, you are at station 1 plus 0, 0. If you are at 250 feet, you are at station 2 plus 50. If you are at a distance from the beginning of 375 feet, you are at station 3 plus 75. If you are at a distance of 465 and 0.50 feet, you are at station 4 plus 65.50. Now, what happens is that a stake is normally set at each station, and they're also set at the point of curvature at the PC, where the back tangent ends and where the curve begins, and of course at the point of tangency, which is the PT, where the curve ends and the forward tangent begins. Now here you see a way to calculate the station for the point of tangency, or the point of the tangent. So the station at the PT is going to be equal at the station at the point of commencement of the point of curvature plus the length of the curve. The station at the PC is going to equal to the station at the point of inflection minus the tangent length. So you have an example. You have station 8 plus 33.20. That is a unique point in the alignment of that roadway. What that means is that point begins 833.2 feet from the beginning of the surveyed line. And what that is also signifying is that the partial length beyond station 8 is 33.2 feet. Another way to use stationing is to simplify labeling of calling out features on a roadway segment. I'll show you a quick example here. 2 stations. So we have station 8 plus 00, which is shown here. And you have station 9 plus 00, which is shown here. This is just on a tangent. But let's say you have a point that you want to figure out where it is here, and another point that you want to figure out where it is here. So because this point is to the right of the alignment, you can say this point is 50 feet to the right, which is typically abbreviated as, maybe I should show the notation, a common notation. Feet are, oops, not 50, 50 feet are, or right, and you are, let's say, at a distance of 25 feet. That means 50 feet to the right of the survey of the road center line. And you are at plus 25. That means you are at station 8 plus 25 feet, which equals 825 feet. This point here will be, let's say, 50 feet to the left and plus 60. So it's another way to simplify calling out different type of stationing objects. You may get a problem in the exam where this nomenclature is shown or something similar to this nomenclature. You just gotta, and then you're asked to somehow calculate the distance between these 2 points or something like that, where you need to use geometry, right? Being this is a horizontal line and the distances are measured perpendicular. From your center line. They're measured perpendicular. So let me symbolize that. Quick square. they are measured perpendicular. So you may be tested with something like that on the stationing. I know that is not directly related to horizontal curves, but it's also related into the geometrics of the different topics that may be covered on the breadth portion of the exam. Or you may be tested in giving you some information like this to symbolize where the PC, where the PT, where the PI are. So you can see stations are a way to separate the 100-foot measurement from smaller measurements. Now, if you want to see a little bit more detail on how stationing is used, you can read section 78.16 of CERN. Now, the PT station is equal to the PC station plus the curve length. In other words, if the beginning point of the curve is 0 plus 0, 0, then your PT equals the curve length. Normal curve layout follows the convention of showing increased stationing from left to right. And we also have the concept of compound horizontal curves, which include two or more curves of different radii. They share a common tangent point, and they center on the same side of the common tangent. PT for the first curve will be the PC for the second curve, which is also known as the point of continuing curve or point of continuing curvature. Compound curve problems are time-intensive to solve, so the breadth portion of the exam is not likely to include them. They can be solved using the same methods used to solve a single curve. However, solving them requires keeping track of multiple curves with varying degrees of curvature and different intersecting angles. Exam problems dealing with compound curves will most likely be conceptual in nature. Like, what is a term for a point where two curves intersect on a compound curve? Oh, that is the PCC. So here's a quick schematic of a compound circular curve. We have two curves that have two different angles, two different radii, and they have one common point where they're tangent at that point. So you have two curves that can only be tangent at the same point, at only one point in space. And that specific point in space will be the PT for the first curve, or be the PC for the second curve. But we don't call it that way, so we simply call it the PCC, the point of continuing curvature, or the point of compound curvature, or the point of the continuing curve, just the PCC, right? Now, compound curves are often used on low-speed roadways, such as on the entrance and exit to ramps on a freeway. So what do you think if we sink our teeth into a problem? Now, this is our second problem of the geometrics lesson. And this is, of course, on horizontal curves. So a horizontal curve is shown with a point of commencement at station 11 plus 56. We have a PT, and we have a radius of 2550, and we have the angle between the two tangents equal to 60 degrees. So we're being asked to find most nearly what is the station of the PT, the point of tangency. Is it 20 plus 26? Is it 25 plus 26? Is it 30 plus 26? Or is it 38 plus 26? Now, if you would like to solve this problem on your own, using the concepts that we have reviewed so far, I will encourage you to go ahead and pause the video at this moment before we discuss the solution. Now, to solve this problem, the best resource that you can have at hand is a one-page summary of of horizontal curves. That one-page summary must include a graphic, the symbols within the graphic, the list and definitions of what each symbol represents in the graphic, and the different equations that you can use to find the different values within the graphic. Having that one-page reference in hand, you will be invincible when it comes to solving horizontal curve type of problems. So let's go to the solution. So there are many ways to solve for the problem. Let me quickly go back. What we're being asked is to find the station at the PT. And we're given the station at the PC, the radius, and the angle between the tangents. We know that the station of the PT is simply the station of the PC plus the length of this arc. That is as simple as that. So somehow we need to find the length of this arc. So we need to figure out what equation will help me use the radius and this angle to find the length of the arc. So you can see PT on the tangent is going to equal my PC plus the length of my arc. So the length of my arc is going to be equal to 2 times pi times the radius of the curve times the angle between the two tangents, my angle of inflection, over 360 degrees. So the length of the curve is 2670.35 feet. Now, to find my point of tangency, I need to add this to my PC. And the best way to convert station into feet is to simply get rid of the plus sign from the middle. Just get rid of the plus sign from the middle, and then you get feet. So we add our feet together, and then we have that's 3,826.35 feet. So how do I convert feet back to stationary? Add a plus sign to the left of the first 2 digits. And that is 38 plus 26. So our answer is D. This is a simple direct application of horizontal curves, and this kind of problem is very common on the breadth portion of the exam. Equation 79.3 for the length of a curve can either be in units of degrees or radians. It is important to pay attention to the units. Sometimes when solving for I, an answer could end up in radians. Please make sure you're using the equation for the angle of inflection that's either in degrees or radians based on the data that you're given in the problem prompt. So here's a hint. When you're developing your one-page resource, please make sure you include an equation to find make sure that any equation that you put in that includes your angle of inflection or any angle is clear to state this, hey, this is in degrees, or hey, this is in radians. So when you're using it on the exam, you're using the right equation. So with that, we're gonna, right at this point, we're very close to, well, we're a little bit over our 1 hour mark, which is okay. And we'll continue with the rest of the geometrics lesson, the last portion of the geometrics lesson, on the next recording.